astronomers just stumbled into a problem they didn't expect. According to one of the most trusted measurements in all of science, our solar system is moving at a perfectly normal pace through space. Nothing strange, nothing dramatic, but a second, completely different cosmic measurement now says that can't be right. It claims we're moving way faster than physics says should be possible. And if that number is real, then either something enormous is pulling us, or one of our core ideas about the universe is missing something big. Here's the strange part. The method behind this discovery is incredibly simple. You already experience it every day without realizing it. When you move forward through falling snow, the flakes hit your face harder than the back of your head. Ride a bike, and the air feels heavier in front, while everything behind you feels calm. Even walking through rain does the same thing. The front gets busier, the back gets quieter. That difference alone tells your brain that you're moving. In cosmology, that exact front versus back effect has a name. It's called a kinematic dipole, and astronomers use it to measure how fast our solar system is moving through the universe. Instead of snowflakes or air, they use galaxies. Extremely distant galaxies barely shift over billions of years. They act like cosmic thumbtacks, frozen in place across the sky. If the universe is smooth on large scales, then the number of galaxies in every direction should be about the same. Left, right, front, back, kit should all balance out. But if we're moving, something changes. The direction we're moving toward should look slightly more crowded. Not dramatically, just enough to notice. It's the same reason rain feels heavier on your chest when you run forward. And by measuring how crowded the sky looks in different directions, astronomers can calculate our speed through space. For decades, this measurement came from one source, the cosmic microwave background. It's the leftover glow from the Big Bang itself, spread evenly across the sky, and it works like a universal speedometer. The tiny temperature difference between the front and back of that glow tells us how fast we're moving. That measurement has been rock solid for years, but recently, astronomers tried something new. They built massive maps of the sky using radio telescopes. Unlike visible light, radio waves pass through dust easily, giving a cleaner view of distant galaxies. By counting how many radio-bright galaxies appear in each direction, scientists expected to confirm the same motion. The CMB has shown all along that's not what happened. One side of the sky turned out to be far more crowded than expected. Not just a little, enough to completely break the math. At first, this looked like a mistake. Maybe a bad calibration, maybe interference, maybe a glitch in one survey. But the strange thing was the direction. The crowded side lined up almost perfectly with the direction we already know we're moving. As if something was amplifying that motion. And that's when the real panic set in, because this wasn't based on a single telescope. Astronomers checked multiple independent sky surveys using entirely different instruments. One of the most important was a massive network of antennas spread across Europe that listens to extremely faint radio signals. Think of it like taking 3 photos of the same scene with 3 completely different cameras. If one adds a weird distortion, the others would expose it instantly. But they didn't. All of them showed the same thing. The dipole measured from radio galaxies was about 3.7 times stronger than what the standard model of the universe predicts. That's not a rounding error. That's not close enough. That's the kind of difference that makes scientists sit back and stare at the numbers in silence. To understand how extreme this is, imagine checking 2 speedometers at the same time. One is the trusted one you've relied on forever. It says you're going 60. The second suddenly claims you're going over 200 in a parking lot. Both can't be right, and that's the problem. The cosmic microwave background says we're moving at a normal speed. The radio galaxy dipole says we're flying through space at a rate that shouldn't exist. So what's going on? The first explanation is unsettling but simple. Maybe the universe isn't as smooth as we thought. Our standard cosmology model assumes that if you zoom out far enough, everything starts looking even. Small clumps average out, big patterns fade away. But this result hints that might not be true. There could be huge regions of space that are slightly richer in galaxies, while others are emptier. Those differences wouldn't be obvious locally, but stretched across the entire sky, they could create a dipole that looks like motion even if it's not. If that's the case, then the radio galaxies aren't lying. They're exposing structure we didn't include in our models. But that leads to an even bigger question. If the universe isn't smooth on the largest scales, what else have we been assuming wrong? And that's where the second explanation comes in. Some researchers believe something enormous might actually be pulling us, not suddenly, not violently, more like a slow, steady tug that's been acting for hundreds of millions of years. The universe is filled with colossal structures, long chains of galaxies, massive superclusters, gigantic voids, and thick concentrations of dark matter. These structures are so huge, they influence the motion of entire regions of space. And here's the creepy part. There's a massive section of the sky we can barely see. It's hidden behind the Milky Way's own dust and stars, creating what astronomers call the zone of avoidance. Our telescopes struggle to look through it, meaning anything sitting behind that region could stay hidden for a very long time. We already know there's a mysterious concentration of mass in that direction called the Great Attractor, and some scientists speculate that something even larger could be lurking deeper beyond it. If that's true, then the strange radio dipole might not be an error at all. It could be the first hint that our entire cosmic neighborhood is being slowly pulled towards something massive. We haven't fully mapped yet. That idea is still unverified, but it hasn't been ruled out. And then there's the third explanation, the one scientists are always reluctant to say out loud. What if the model itself is incomplete? A cosmological model is just a set of rules, a recipe that explains how matter, energy, space, and time behave together. Our current model does an incredible job explaining dark matter, dark energy, galaxy formation, and the expansion of the universe, but it expects consistency. When one number refuses to match the others, that's not something scientists can ignore. It doesn't mean physics is broken. It means the rules may need updating. This radio galaxy result behaves like a stubborn variable that refuses to fit into the equation. And when that happens, history shows that science usually changes the equation, not the data. So what happens next? Luckily, astronomers won't have to wait long. A new generation of sky surveys is coming online, not built specifically to solve this mystery, but powerful enough to test it naturally. The square-kilometer array will map the radio universe deeper and cleaner than anything before it, and the Vera C. Rubin Observatory will track galaxies across time with unprecedented precision. With better data, scientists will find out whether this extreme dipole holds up or quietly fades away. If it's real, then something massive is shaping our entire region of space, and if it's not, we'll have learned just how easy it is to fool ourselves when reading patterns written across the sky. Either way, the universe just reminded us of something important. Even after centuries of study, it still has the power to surprise us, and sometimes, the most unsettling discovery